Good day, Doctor. We are from Group 3 and we would like to present our experiment project titled on Faraday's Law of Electromagnetic Induction.
In today's world, Faraday's law plays an important role in our life. For example, transformers. A transformer consists of two coils wound around a core. When alternating current flows through the primary coil, it produces a time-varying magnetic field within the core, and this changing magnetic field induces an EMF in the secondary coil. And second, generators, a device that converts mechanical energy into electrical. A conductor coil is rotated between the poles of the magnet, and the rotating coil intercepts the magnetic field and the current is induced in it. And last, induction cookers. An induction cooker is work based on mutual induction, which also derived from the Faraday's law. When the AC current passes through the coil, it generates a changing magnetic field which induces an eddy current in the base of the pan, and then converted into heat, allowing the food to cook without a flame. In this project, we aim to demonstrate a simple experiment to prove the concept of the Faraday's law. Before we proceed, let's explore the theory behind the Faraday's law.
Next, I want to present the theory for this experiment, which is Faraday law. Faraday law of electromagnetic induction is a fundamental principle in electromagnetism that explains how an EMF is induced in a coil or conductor when it is opposed to a charging magnetic field. There are two conditions that lead to induction, which is shown in our experiment. First is a stationary conductor placed in a time-varying magnetic field and a moving conductor within a static magnetic field. According to Faraday law, the induced EMF is directly proportional to the rate of change of magnetic flux and the number of turns in the coil. It's expressed as a formula that's set in the picture. And V is equal to the induced electromagnetic force, and N is equal to the number of turns in the coil, and flux is the magnetic flux through one loop. And the negative side indicates the direction of the induced EMF, meaning it opposes the change of magnetic flux. We will present the apparatus and material for this experiment.
We have prepared the materials and apparatus needed for the experiment, including a multimeter, sandpaper, connecting probes, a bar magnet, enamel copper wires, and a lighter. Experiment carry out some pre-lab preparation. First, we prepare solenoid with different number of turns, specifically 50, 100, 150, 200, and 300 turns by coiling the enamel copper wire. Then, we burn the enamel insulation at both ends of each wire using a lighter, and scrape off the char residue with sandpaper. These steps were done to ensure that the wire ends were conductive. Moving on to the procedure of the experiment. First, we connected the two ends of the 50-turn solenoid to a multimeter using the probes. Next, we quickly insert and remove the bar magnet through the center of the coil. We then observe and record the magnitude of the induced voltage. After that, we disconnect the 50 turns of solenoid and replace it with the 100 turn solenoid. Step 2 and Step 3 were repeated using the 150 turn, 200 turn, and 300 turns of solenoid. Proceeding to the result section, here are the readings for the 50 turn solenoid. And followed by the results for the 100 turn solenoid. The next are the results for the 150 turn solenoid. And 200 turn solenoids. Lastly, we present the result for the 300 turn solenoid. From the observation, we can clearly see that the magnitude of the induced voltage increases as the number of turns in the solenoid increases.
In this section, we'll discuss the findings from our experiment on electromagnetic induction. The objective was to investigate how the number of coin turns affects the magnitude of the induced voltage. As we increase the number of turns in the coin from 50 up to 300, we observe a clear and consistent increase in the voltage readings on the digital multimeter. For example, with just 50 turns, the induced voltage range between 0.1 and 0.6 volts. But when we use 300 turns, the induced voltage increased significantly, ranging from 3.7 to 5.8 volts. This proves Faraday's law of electromagnetic induction, which states that the induced EMF is directly proportional to the rate of change of magnetic flux and the number of turns in the coin. The results confirm that a coin with more turns can generate a higher voltage when exposed to a moving magnetic field, as each loop contributes to the total induced EMF. These voltage values were recorded directly from a digital multimeter connected to each coin. The increasing trend supports our hypothesis and matches theoretical expectations. From the graph, we can also see a clear upward trend, which is from 50 turns, 100 turns, 150 turns, 200 turns, and 300 turns. This illustrating the linear relationship between the number of coin turns and the magnitude of induced voltage.
In conclusion, Faraday's law explains how electricity can be generated through the motion between magnetic field and the conductors. Our simple experiment, a stationary coil and a moving magnet, show that the changing magnetic field can induce a voltage. And the experiment also showed that a coil with more turns produces a stronger EMF, which aligns with the Faraday's law, states that the induced EMF is directly proportional to the number of turns in the coil. Thank you for watching our presentation.